Alright, welcome back to our CNT140 class lecture video for Chapter 11, Fiber Optic Techniques. In this lesson, the objectives we will be highlighting will be fiber optic basics, fiber optic cable configurations, fiber optic connectors, structured centralized fiber, equipment considerations, safety considerations. Now, fiber optic has an important place in LAN wiring. Fiber can generally support faster applications over longer distances in copper cabling. Fiber is also the first medium chosen for implementing new high-speed technologies such as gigabit and 10 gigabit Ethernet. Fiber optic cabling occupies an increasingly important place in the networking arena, and it is important to understand this key of technology. Optical fiber was initially used for intercity telecommunication links to replace antiquated and overloaded microwave links at a lower cost than satellite. In this application, T-carrier links and later SONET links provided extensions of the telecommunication services over long distances. The intercity fiber featured advantages of long range, wide bandwidth interference immunity, and relatively low installation costs compared to the bandwidth provided. In fact, it was the lower cost, relatively high bandwidth fiber optic technology that fueled the modern wide area communications revolution. In the wide area, the availability of right-of-way for fiber cable installation was the key to building a fiber network. One of the earliest implementers utilized partnerships with railway companies to place fiber along rail lines from coast to coast. International communications also benefited from this technology, as literally thousands of fibers of fiber optic cable were placed along the ocean beds between continents. The development of this high-volume intercity fiber network required significant advancements in the technology of both optical fiber and optical transceivers. As the technology moved forward, devices and materials became available for use in the bandwidth-hungry LAN domain as well. Now, LANs have quickly adopted faster data transmission technologies during the same period of time, and these data topologies, such as gigabit and 10 gigabit Ethernet, require high transmission bandwidths and have really put twisted pair copper to the test. Fiber optic cable, in contrast, has a vast superior bandwidth capability, particularly at the shorter distance that's prevalent in LANs. The focus of this chapter is to provide a concise explanation of the utility of fiber optic technology in the LAN environment. We'll explore the facets of fiber optic technology as they relate to LAN applications. Now, some of these topics will overlap wiring technologies that are covered in other parts of the book, and we will repeat the key points here with reference to chapters in the book for supplementation where they're appropriate. Fiber optic components are an integral part of structured cabling and may be used in concert with copper components, with each technology doing what it does best. So let's look at the fiber optic basics. Before we delve into the LAN applications, let's review the basics of fiber technology. We need to understand how optical transmission works and what the key terms and parameters are. The phenomenon of the transmission of light through fiber optic media comes from the optical principles of refraction and reflection. Now, as you know, a beam of light bends when it passes from one medium into another. The most familiar example of this is the air-water transition. Fill a pan with water, place a coin at the midpoint of the pan's bottom. Now stand back from the pan and place a straw or pencil into the water along your line of vision to the coin. The straw appears to bend upward from the straight line at the surface of the water. Now place a straw into the water from the right or left side, and you'll see the same upward bend. The straw is obviously not bent, but the reflected light from the part of the straw between the water surface has bent at the air-water interface, making the straw appear to bend. This bending of light as it passes from material to material is called refraction. Materials that transmit light have a property called the index of refraction that is proportional to the amount of bending that would occur between a given material and a vacuum. Now, both air and water have respective indexes that indicate this type of behavior. Now, while the air-water refraction is trivial unless you're spearfishing, the same refraction principle is used in forming lenses, such as those used for vision correction. and can be used to culminate light as well. Now, as the figure behind me shows, the path of a ray of light bends at the interface between two transmissive materials. The amount of the bend is determined by the index of refraction. However, beyond a certain incident angle, called the critical angle, the ray of light is reflected from the interface rather than refracted into the medium. That is exactly the reason that the coin in the water seems to disappear when you try to view it from a low angle to the water's surface. By the way, the angle at which the light is bent depends on the wavelength or color of the light, which is how prisms and rainbows work. This phenomenon actually causes lots of problems for multimode fiber, as we'll see later. Now, for years, we concentrated on the incident angles that were necessary for the effective transmission and refraction of light from one medium to another through the interface. Now, this was useful for the design of eyeglasses, binoculars, telescopes, and microscopes. However, if the transmission medium is formed into a solid strand of glass or plastic, we can use the reflective and refractive principles to guide the rays of light within the strand along its length. Now, carefully constructed fibers of glass or plastic can efficiently transfer light for longer distances or long distances along their length, with very little loss of light outside that fiber. Now, you're probably familiar with the decorative lamps made with hundreds of short plastic fibers, and the fiber strands glow very slightly along their lengths, and when a light source illuminates, the strand ends placed at the base of the lamp, but the fiber end shines more brightly. Now, similar fibers are used to transmit light along the network pathway of lamps. We simply modulate or vary the light beam in order to carry data. Optical fibers can be either glass or plastic, but for most of this discussion, we'll refer to the fiber optic material as glass, since silica compounds are used in most current LAN applications. These silica fibers are sometimes called light pipes because light seems to be conducted through the flexible fiber, just like water through a tube. Now, optical fiber is not actually a pipe for light. As stated previously, light passes through the glass, not through a pipe formed from the glass. The refractive properties of the glass are used to direct the light through the center portion of the fiber, and as shown here behind me. Now, depending on the type of fiber core, the incident light beam reflects or refracts its way down the length of the fiber, staying roughly in the center portion of the core, much as water in a pipe would. Now, an appropriate light source is used to send a communication signal through the optical fiber. Now, here's how data transmission over fiber works. A data modulated electrical signal, such as a LAN packet, is first applied to the light source, which converts the signal into light. The beam of light from the source is then directed at one end of the fiber, which transmits it through the fiber all the way to the other end. At the far end of the fiber, a light-sensitive device is used to then detect the light from the fiber and convert it back to the electrical signal. The device that actually creates the light is called the source, and the device that receives it is called the detector. Light-emitting diodes and laser diodes use two examples of semiconductor light sources that are used in fiber optics. Photodiodes and phototransistors are examples of fiber optic detectors. Now, the entire portion of circuitry that converts the electrical signal to light is called simply the transmitter, and it includes the light source. Likewise, the circuitry that detects the incident light and converts it back to the electrical signal is called the receiver, and it includes the light detector. In many fiber applications, the transmitters and receivers are actually pre-packaged devices that are simply mounted on the circuit board of the optical equipment. Most fiber optic interfaces are technically simplex connections, that is, either for transmitting or for receiving, but not both. Two interface connections, one for transmit and one for receive, are required to make a complete connection. This two-connector arrangement forms a duplex connection. Now, the optical connections to an equipment interface are thus paired and are usually marked TX or RX, or T or R for transmit and receive, to indicate the transmit and receive directions respectively. Taken together, the transmit and receive optics are called an optical transceiver. Some optical connector pairs are arranged with an exact spacing so that a pair of optical plugs can attach simultaneously. Fibers are terminated in two separate plugs and then snapped into a duplex adapter. Both the 568SC connector and the so-called SFF connector specified in the 568C are duplexed this way. Paired fiber cords, called duplex cords or zip cords, are normally used for fiber optic jumpers. The cords can be terminated in the appropriate type of fiber optic connectors for the application. For transmission over the fiber, the light from the optical source may be culminated into a narrow beam to more efficiently couple its energy into the fiber. In the case of the laser sources, the light beam is already quite culminated and must simply be aimed accurately at the fiber core. As a matter of fact, the coupling of the optical source and the interconnection of the terminated fibers are critical parts of fiber optic transmission technology. If the termination is properly done, the connector hardware will normally ensure that the fiber-to-fiber or fiber-to-source coupling is maximally effective, resulting in an absolute minimum coupling loss. Let's take a look at the different fiber types. Optical fiber is available in both glass and plastic compositions. Glass is the most prevalent in land uses because of its inherently greater bandwidth. Several uses for plastic fiber exist, and this is an area that has had more development over the past several years. However, at this point in time, the higher bandwidth and longer distance requirements of modern networking still demand the use of silica-based fiber in most applications. The fiber's core actually transmits the light's beam, while the cladding provides the strength, flexibility, and a controlled stop in refractive index. All are necessary for proper fiber operation. Do not mistake the cladding for the plastic buffer and the primary coating that coat the fiber strand in a tight buffered cable construction. The buffer and the primary coating are removed by a stripping tool in preparation for termination of a strand. The cladding, on the other hand, is an integral part of the fiber strand and cannot be removed. Optical fiber is also available in two modal compositions, single mode and multi-mode. Described in the light modes that each will propagate, as you can see behind me. Single mode has a very narrow core so that only a narrow beam of light can propagate down the fiber, essentially in single mode of light. Multi-mode has a much larger core diameter and multiple modes of light propagate either by reflection from the core walls or by a combination of reflection and refraction in the core. As the table behind me shows, optical fiber types approved for LAN wiring. Single mode fiber used in LAN technology has a core diameter of only 4 to 8 UM and is surrounded by a cladding that is generally 125 UM in diameter. Multi-mode fiber used for LANs has a relatively large or large core that is either 50 or 62.5 in diameter. Again, surrounded by a cladding of 125 in diameter. Now these dimensions hold for most LAN and campus fiber that's currently in use, although a variety of other types are available for other applications. Multi-mode fiber is further subdivided into two primary types, step index and graded index fiber. These terms refer to the gradation of the refractive index as measured radially from the center of the core. And as you can see behind me, the rays of the light bounce off the walls formed by the radical step and refractive index between the core and the cladding of the step index. In contrast, in graduated or index mode multi-mode fiber, the rays primarily bend because of the gradual change in refractive index from the center of the core to the edge of the cladding. Now, if we look at some fiber optic cable configurations, the cables are available in a wide variety of physical constructions. Fiber cable can be anything from simple 2-fiber zip cord used for jumpers to 144 fiber cable, often layered in rows of 12 for intercity transmissions. Cable for outdoor use, called an outside plant, may have an integral steel cable or even a jacket armor to resist rodents. However, most of the fiber used in LAN wiring is ordinary indoor rated multi-fiber cable of 1 or 2 configurations. This discussion supplements the information that we had in Chapter 5, which is wire and cable technologies for the LANs. Tight buffer cable, one of the 2 main fiber cable constructions, is called tight buffer. Now, as you can see behind me, it illustrates a single strand cable. The buffered layer is between the fiber's primary coating and the outer strength and jacket layers. In a tight buffered cable, the buffer is a plastic coating that separates the bare fiber from these outer layers and protects the fiber as the outer layers are removed. A multi-fiber tight buffer cable has 2 or more of the buffered fibers, which may be additionally covered by an individual jacket and one or more spacer or strength members. During installation or termination of the outer the outer jacket and the fine strands of the strength layer are removed with a sharp blade or a cable stripping tool, leaving what appears to be a small diameter flexible strand. Now, this strand is the bare fiber consisting of the fiber core, cladding, and primary coating, plus the tight buffer. A precision tool, which is basically like a wire stripper, is used to exactly cut the buffer sleeve without nicking the bare fiber. The plastic buffer is then removed by gently pulling a stripping tool toward the cut end of the fiber. The plastic primary coating may also be removed during this process. The fiber is then cleaned with an appropriate solvent, such as alcohol. After some additional steps, the remaining bare fiber is then trimmed, terminated into an appropriate fiber connector. Tight buffer cables are often used where a small number of fibers are to be pulled between 2 points without the use of a protective raceway. In these applications, the cable usually includes a tough outer jacket. The dual or duplex or zip cord type of cable is also used for patch cords, user cords, and jumpers. At the interconnection location of a multi-strand tight buffer cable, you must be careful to provide proper strain relief for the main cord and the individually connectorized fibers. In many cases, the jacketed cable is very stiff, while the bare fibers are extremely flexible, yet quite fragile. Then, if we have a tight buffer cable, we're going to have a loose buffer cable. And in a loose buffer cable, 1 or more bare fibers, fiber with the primary coating, are placed loosely in plastic tubes, as you can see behind me. Several tubes may be placed together with strength members and fillers inside a plastic outer jacket. Now, because of the construction of the cable, it is often referred to as loose tube cable. From 1 to 12 fibers are generally placed in each tube. Hybrid cable constructions may place both multi-mode and single-mode fibers in separate tubes. At the end of the cable, the outer jacket and strength layers are removed. Any filler or central structural members are cut and discarded. The tubes are then carefully cut to an appropriate length for terminating, and the individual fibers are prepared for and terminated in the appropriate connectors. Strain relief, fiber routing, and excess fiber storage are provided in the fiber termination tray. The loose buffer fiber optic cables are most often used in multiple fiber runs between distribution points, such as telecommunications rooms. This type of cable is appropriate for structured cabling, backbone cables for campus backbone runs, and for runs to the multi-user telecommunications outlet assembly in our open office environments. Centralized cabling systems may use this type of cable effectively to run to a point of interconnection, such as a telecommunications room on a building floor. Individual cables may then be run to each user outlet. The major advantage of loose buffer cable construction is that it takes less time to terminate the same number of fibers than with tight buffer cables. An application with a relatively small number of fibers will not see much difference, but an installation with large numbers of fiber terminations will go much faster with loose buffer construction. In addition to the inside plant cables, several types of loose buffer cables are offered for outside plant. A non-metallic direct burial cable, sometimes called a dielectric cable, is one type. This cable is somewhat more impervious to lightning damage, but be assured that if the cable is run alongside metallic cables, as is frequently the case in aerial runs between telephone poles, a direct lightning strike will blow a hole in this type of cable just the same. An interesting technique wraps a steel wire around the length of the non-metallic cable to add strength to the cable runs between the poles. Outside plant cable may also be duplexed with a steel cable called a messenger cable for aerial installations. For direct burial applications, a metal armored cable is used. The armor is often a wound layer of copper, steel, or lead tape that is placed between two outer jacket layers. Now let's talk about the fiber optic connectors. Now the fiber optic technology is notable for its use of an incredible number of incompatible connectors. And in defense of the fiber industry, traditional fiber optic applications have been more esoteric than copper applications. And the interactions of the fiber, the connectors and the transceivers, have been far more complex and subtle. Now this has resulted in a parade of improved connection technology that has attempted to address a progression of assembly, usage, and alignment. Problems that have arisen over the years. Now, fiber connectors have tended to be redesigned to meet performance and convenience objectives, rather than the radical technology changes of copper networking. As the table shows, there's some of the more popular fiber optic connectors listed in approximate order of the introduction, except for the SFF connectors, which have all been introduced about the same time, and a surprising number of the legacy connectors that are still in use. Now, the latest issues that have demanded further modifications of connectors standards are the pluggability and the duplexing. Now, prior to the A revision of the 568 of the TIA-EIA, the SMA and ST connector types were in common use. Now, the SMA is a threaded single fiber connector, whereas the ST is a bayonet, which means you push on, turn, and lock it. Single fiber type connector. Now both are rather like miniature optical versions of the type N and B and C connectors that we are familiar with from the early days of Ethernet. Now unfortunately, the SMA and ST connectors had to be mated to corresponding chassis or patch connectors individually, even if the connectors were somehow marked or color coded. It was quite possible for the connectors to be reversed, mixing up transmit and receive, and then causing the link to die. Now, as all fiber interfaces consist of two connections, a connector type that could be paired was unneeded. The initial solution was the SC connector, which was designed as the preferred connector of the 568A revision of the standard. The SC connector had the advantage of a push-to-mate, pull-to-unmate connection that allowed two connectors to simultaneously plug into an interface. Now, when two SC connectors are linked by a clip, which aligns to the pair and allows them to be plugged in as a unit, the assembly is designated as 568SC. The SC connector also continues to trend toward click termination fiber connectors. Now, such connectors typically use a combination of no polish crimp bond construction to speed up the termination time to as little as 60 seconds per connector. These quick termination connectors drop the time consuming step of epoxy bonding the fiber to the connector by using a crimp-on system, somewhat similar to coax cable connectors. The main difference is that the fragile glass fiber absolutely must not be deformed during the crimping process, or it may fracture or break. In addition, some of the new connector implementations now use a pre-terminated connector arrangement. Now, as you may know, one of the most time-consuming steps in a conventional fiber optic connector assembly is the polishing of the end of the terminated fiber that pokes through the tip of the fiber connector. The style of pre-terminated connector has a built-in pre-polished fiber stub at the tip of the connector. The bare fiber strand is inserted through the back of the connector and into a special matching fluid that closely matches the index of refraction of both fiber pieces. The result is that the usual deflection of the incident light rays that would occur at an angled fiber end is essentially absent. Instead, the beam passes into the matching fluid and then into the fiber stub with virtually no refraction, eliminating a very time-consuming step from the assembly process. An alternative process uses an indexed matched optical quality sphere to minimize the light dispersion at the end of the fiber and direct it to the pre-polished fiber stub. However, there is sometimes a price to pay in using the quick termination fiber connectors. A standard cut and polished fiber termination normally has a lower connector loss than the quick termination type, or the small FF or small form factor connectors. The small form factor connector is the very new type of fiber optic connection. Now, although the SC connector met the push-pull and duplex criteria, it was a large connector that required two adjacent slots in a modular faceplate. Patch panels had to be completely redesigned to fit this connector, and it prevented the high density arrangement needed for fiber blades in switches, hubs, and routers. The connector of the SFF was put forth to remedy the size problem. The SFF connector is generally defined as a fiber optic connector that terminates two fiber connections within the form factor of a single insert in a modular jack plate. This arrangement generally complies with the requirement to align a duplex fiber connection. The TIA 568C optical fiber cable and component standard drops the requirement for a specific connector on the basis that this will encourage innovation and that the market will determine usage. The connector can be of any configuration that meets certain requirements and does not have to be exactly like the copper modular RJ type connector. The figure behind me shows some of the more popular SFF connector types in contrast to the conventional 568SC connector. Now, there are two major requirements that must be met by any SFF connector that complies with the 568C. First, or C.3. First, the alignment of the optical components must meet the applicable FOCIS 5 document. And second, the connector must allow the two-position AB orientation of the standard to be maintained. This orientation is explained in detail back in Chapter 7. The basic concept is that AB orientation is reversed at each end of the interface in such a way that the transmit-receive relationship is maintained absolutely throughout any sequence of the cable and patch cord interconnections. The system automatically creates a crossover between transmit and receive at the equipment interfaces at each end of a run. The SC connectors and adapters must be oriented in a particular manner to preserve this relationship, and they are still often used to illustrate the arrangement. The SFF connectors automatically orient themselves because each fiber is permanently placed in its location in the connector. However, this does make pair reversals harder to remedy, as one cannot simply unclip and reverse the SCs. The SFF connectors may also include a latch, as with the 8-pin modular RJ45 or RJ connectors. The use of a latch simplifies the AB orientation will be maintained because the plug can be inserted only one way. On the other hand, it's up to the connector/adapter manufacturer to indicate the AB connection polarity to the installer. Since the whole fiber interconnection system of the TIA is organized to create a consistent reversal at each adapter, all of that must be maintained. Next, we want to talk about connector codes. The TIA 568C.3 requires a different color for connectors and adapters according to the fiber mode. Multi-mode components are required to be beige, while single-mode components are required to be blue. Now, this can eliminate an enormous potential problem in identifying which type of fiber is present. Fiber mode mismatch can cause 4 to 6 dB loss one way and can cause a system to fail or to be unreliable. This relationship is so important that we've repeated it in table 11.3 behind me. Now, installers and network managers should ensure that they use the proper color code to indicate fiber mode on all connections and patch cords. However, there are no special keying or connector differences to prevent mating single mode to multi-mode, if that is really what you try to do. But you should easily be able to see the color mismatch if the color code is then followed. Now, if we look at the optical fiber bandwidth, in multi-mode fiber, the most significant factor that limits the link distance is called optical bandwidth. And this term is a bit of a misnomer, as what is meant is the capacity for information transmission. As with many of the optical parameters, there are significant differences between the commonly used coax cable transmission terms and their corresponding optical lingo meanings. The actual theoretical bandwidth of a signal that can be carried on a fiber strand is extremely high, on the order of 50 to 300 gigahertz for short lengths. In practice, a system's bandwidth is determined by the wavelength, the optics, the electronics, and the connecting hardware, the fiber, and the circuit length. Now, as the figure behind me shows, some typical system bandwidth versus cable distance curves on single mode and multi-mode fiber. Now, as you can clearly see, there is a vast performance difference in the system bandwidth between multi-mode and single mode fiber types. Multi-mode fiber, as the name implies, allows the propagation of many light modes, which gives rise to chromatic and modal distortion. This distortion of the light signal severely limits the information capacity of multi-mode fiber. The minimum performance standards are shown behind me, and the useful bandwidth of a particular cable length can be inferred by dividing the stated bandwidth distance product by the actual length in kilometers. Thus, from the table, a 100-meter fiber run of 50 to 125 UM can be seen to have a 500 megahertz kilometer divided by the 0.1 kilometer. So we'd have a 5,000 megahertz effective bandwidth. On the other hand, a 220-meter run of 62.5 125 will have a 727 megahertz effective bandwidth, which could cause a real problem for gigabit Ethernet. Now, if we refer to Chapter 12 for a complete discussion on the fiber cable lengths that are supported by gigabit and also 10 gigabit Ethernet. The system designer faces something of a dilemma in specifying fiber optic cabling for use to a workstation outlet. On the one hand, multi-mode fiber is less expensive and supported for more current types of workstation and hub equipment. However, single-mode fiber has an information bandwidth that is vastly superior and might be usable for many more years. Now, in addition, now that most of the equipment optics for high-speed networking are laser diode based, the assumed cost advantage of multi-mode friendly LED sources is essentially nil. So the problem is whether to specify less expensive, more common multi-mode fiber to the desktop, or to use single-mode fiber. The single-mode fiber has the opposite disadvantages, but will have a significantly higher bandwidth for future network growth. However, single-mode fiber alone is incompatible with much of the current networking equipment. The answer that many are realizing is that you can do both. The standard specifies a minimum of 2 cables to each work area outlet, one of which will be fiber. However, it does not prohibit placing more than 2 cables to a work area. Virtually all modular cover plate designs allow at least 4 module inserts. So the optimum solution for today and the furniture is to place 2 copper cables and 2 fiber cables, single mode and multi-mode, to each outlet box. If you use the new SFF fiber connectors, the Cat5e or Cat6 copper modules, you should be set for applications many years to come. Now the VCSEL laser source multi-mode problem. A popular laser source for high-speed networking is the vertical cavity surface emitter laser. Now this semiconductor diode combines high bandwidth with low cost and is an ideal choice for the gigabit networking options. In a single mode fiber environment, the laser source works flawlessly. Its highly culminated beam of light is easily aimed right down the center of the narrow single mode core and propagates in essentially a single mode of transmission with all the attendant advantages. However, as we just covered, much of the installed fiber in the local network is actually multi-mode fiber. Back when we were using LED sources for the lower speed technologies, such as 10 base FL and 100 base FX, we simply aimed the LED at the transmit end of a multi-mode fiber and we just let things happen. In effect, the excess light did not fill the core, it was just then lost. But the light that did not enter the core of the fiber propagated along the core in all modes, thus the term multi-mode. Now the method of applying the source light to the fiber is called the launch, and applying more light is needed in an overfilled launch. Unfortunately, when multi-mode fiber was made in the past, little attention was paid to minor defects in the glass core. If multiple nodes are launched into the fiber, a tiny aberration here and there causes little harm because of the other modes or rays of light that would get through just fine. At most, these defects might cause a small increase in cable attenuation. Nothing to be worried about unless you launch with a laser source. Now remember that a laser is an extremely narrow beam of coherent light on the order of 1 UM for most VCSELs. That is launched precisely down the center axis of the fiber core. This means that any minor defect may deflect a substantial amount of the available light energy, causing an excessive amount of attenuation. This may in turn cause a link failure in the system. Its system can't tolerate an extra 2 or 10 dB of loss. Worse yet, minor deflections of the fiber, which might be caused by mechanical movements or even temperature changes, can cause the link problem to be intermittent. Two solutions exist to what has been dubbed as the VCSEL problem. One is to get better fiber. Certainly, if you're installing new cable, this is the best option. You must be sure that the fiber cable you specify is rated for laser operation as well as extended bandwidth, the bandwidth distance product. Such fiber is often called gigabit ready or laser compatible. If you have existing multi-mode fiber, you may have to use a short conditional launch adapter to spread the single mode laser source to multiple modes. The bad news is that the adapter may add an extra $50 to $100 to the cost of your installation. Now, if you suspect that there may be a problem with your older multi-mode cable, you may still be able to use 1000 base SX, as many of the transceivers for this technology include built-in mode conditioning. You're going to want to check with your equipment manufacturer for that one. Standardized fiber optic LAN cabling. The basic principle for the standardized cabling infrastructure is predictability. A strong measure of network integrity and reliability can be realized by utilizing a standards-based cabling system. Much has been said about the value of providing a structured cable plant that meets recognized standards for copper cable installations. A standards-based installation for fiber optic cabling is just as important. Manufacturers' networking equipment depend on the cable standards of the TIA and the operating standards of the IEEE, among others, for the compatibility and performance parameters of their products. The cabling designer and network manager depend on these standards as well. With an inside cable plant that is designed and installed according to the standards, you can be assured that the equipment you purchase will operate properly to the limits specified. Actually, the two types of standards work in concert to bring the performance of the network up to the necessary levels. The TIA committees carefully consider the existing and planned LAN technology innovations when they create their cable standards. And likewise, the IEEE standards committees consider existing and planned cabling standards and the ability of emerging networking technologies to use these widely deployed cabling plans. Initially, the network technologies that were to be supported required modest performance parameters to support networks with 10 to 20 megahertz bandwidth. However, the speed target has moved rapidly upward until we find the standards now supporting link testing limits of 100 megahertz to 250 and even 650 megahertz. Now, as the cabling standards have moved forward, the ability to place these higher speed networks on the cable plant has advanced as well. Fiber optic cabling is an important part of cabling technology and adds to the wealth of options available to the network technologist. Although fiber optic cabling has an inherent bandwidth advantage over copper in many applications, it's still subject to standards of installation and operation, from the connectors to the very fiber itself. Every feature of a fiber link must be appropriate for the application and for the equipment with which it is used. For this reason, we will spend some time describing the two types of fiber optic cabling standards that are currently in use. These standards are the structured cabling system and centralized cabling structured fiber cabling, the TIA standards. The tried and true method of fiber connection is the structured cabling systems conceptualized in the 568C. And as you recall, this standard allows for both single mode and multi-mode fiber. Although the earlier A version really encouraged the use of multi-mode in the horizontal structure, the single mode is in the backbone. Multi-mode fiber and the lower speed LED optics have traditionally been less expensive than single mode fiber and laser optics, and as a result, much of the fiber that has been installed in conformance with the structured cabling pattern is multi-mode. Multi-mode fiber as structured in the structured environment works equally well with Ethernet, fast Ethernet, and gigabit Ethernet. This is quite an accomplishment when you think about it. Part of the reason for this high-speed compatibility is the 90-meter horizontal runs of structured cabling. This short distance limit is really dictated by attenuation and crosstalk parameters of twisted pair cable when tested to 100 megahertz. It is no small irony that fiber advocates can thank the use of Cat5e copper cable for this relatively short run and the consequent longevity of multi-mode fiber. The game now is to standardize multi-mode for 55 and 100 meter runs for 10 gigabit Ethernet. Now, as you can see behind me, backbone cabling runs are made from a central distribution point, such as the main cross connect, to the telecommunications rooms throughout the building. Now, at each TR, a fiber hub or switch distributes the network signal to individual horizontal fiber runs, one per workstation to be served. An optional multi-user telecommunications outlet adapter may be placed in the horizontal run between the TR and the work area outlet and connector. Now, as explained in Chapter 10, when open office wiring practices allow the use of the fiber optic MUTOA, which is the multi-user termination outlet connector. In the strict sense, the run from the MUTOA to the workstation is supposed to be a user cord that plugs directly into the workstation. However, the designer may wish to use a fixed workstation outlet adapter to protect the long fiber run back to the MUTOA. This is not permitted for copper cables, primarily because each termination and interconnection adds significantly to the crosstalk problem. With good fiber terminations, only a few tenths of a decibel of an additional link loss are added, and the additional interconnection of the WOA is generally insignificant. In addition, the potential for damage to the duplex fiber cord is greater than with the more robust copper cord, and it would be tedious and costly to replace a damaged user cord all the way back to the MUTOA. So if we talk about centralized fiber cabling in the TSB72 and the TIA 568C, fiber optics can support distances far in excess of those which copper pairs fail to work. In recognition of this fact, it is often possible to make a fiber run all the way from a central equipment room or MC directly to the work area. The topology shown here is what we're talking about. In this arrangement, the structured approach is abandoned for the fiber connections and is replaced by centralized fiber cabling. Centralized fiber has two primary advantages. The cost of each run is presumably less because the system eliminates at least two connectors for each run, along with associated termination costs and the cost of a patch panel on each TR. In addition, a centralized fiber hub may be used, presumably at a lower cost, and a better port usage than would be the case with the hub in each TR. The centralized hub also simplifies administration and management. Centralized cabling was first described in the TSB 72, the Centralized Optical Fiber Cabling Guidelines. And this telecommunications bulletin supplemented the 568A to add design parameters for the use of centralized fiber runs. The -B and C revisions of the standard incorporates this information. And in practice, the centralized fiber cables are routed through existing TRs, even though there is no termination or equipment hub there. The reason for this practice is that the TR is frequently the location of the interfloor ports that physically connect to the MC or other point of consolidation. In addition, if a blown-in fiber system is used, the multi-cell tubes may be run to the TR where they are broken out into individual tubes and routed to each work area. Alternatively, loose buffer multi-fiber cables may be run to each TR and then spliced onto individual work area fiber runs. This method avoids the additional bulk cost and loss of an interconnection patch panel. The splices are allowed in fiber runs, unlike copper runs, as they add insignificant signal degradation to the optical path. The TR splice method may be used in blown-in fiber systems as well as in a hybrid system, which would use loose buffer cables to the TR and blown-in fiber tubes to the work area. As with the structured system, you may use multi-user outlet consolidation to open offices as stated before. All fiber systems are inherently interconnect systems rather than cross-connect systems. And from a practical standpoint, it matters not where the interconnection occurs, so the MUTOA takes the place of an interconnect in a TR in the centralized fiber layout. Centralized fiber cabling is a viable option for any fiber cable installation. Care should be taken that the total run length is within the operating parameters of the networking technology that you're trying to support. For example, certain fiber runs may be limited to 220 meters for gigabit Ethernet, so you would want to stay under that length. However, with the right multimode fiber, you can use two new standards, the 10G base SR and 10G base LX4, to support 10 gigabit Ethernet to up to 300 meters. Now with single mode fiber, though you can get up to 10 kilometers using the 10 gigabase LR, if standardized fiber does not have a limitation, it has the ability to handle future increases in network bandwidth. Now remember that the current crop of legacy fiber in the horizontal cabling is miraculously able to support gigabit because of the short horizontal limit of structured cabling. Newer, laser-friendly multi-mode and single-mode cable is still an overkill at 90 meters for gigabit, but it might be just right for 10 gigabit operations. A measure of future proofing can be obtained by at least running your centralized fiber through a TR. Then, if you absolutely must have shorter fiber runs to support future technology, you can cut and terminate the fiber runs within the TR and place your hub equipment there. Standard fiber optic network links. Now, fiber is used for a wide variety of network connections. Now, many of these are described elsewhere in our lessons, including Chapter 6 and 12. However, some of this information is repeated in the table behind me to illustrate the wide variety of purposes to which fiber optic cabling can effectively be utilized. fiber optic equipment considerations, the network equipment you use with structured fiber optic cabling must be compatible with the installed fiber in order to function. You may need to use simple connector adapter cables with one end matching the network or workstation equipment and the other end matching the outlet or patch panel connection. In addition, you may need to adapt between the different technologies such as single mode and multi-mode, or copper and fiber. Just what are these issues and how can you deal with them? Well, fiber to the desktop. The watchword in the fiber cabling industry is fiber to the desktop. In the early days of networking, this was seen as an ability to offer almost unlimited bandwidth to the user, or at least to the user's workstation, as few of us had much bandwidth at the time. Now, the most popular option for this desktop fiber was the OC3, which is 155 meg per second. Now, this connection was primarily suggested because the 10 base F options were not considered high speed, and the 10 meg data rate could easily be supported on legacy Cat3 wiring. However, a more practical problem that existed with OC3 was that it primarily used ATM, which was a rare protocol in the local area and not very well supported by software hardware manufacturers. FDDI was also available as a desktop option, but an interface cost that frequently equaled or exceeded the cost of the equipment it was connecting. The 100 base FX and any of the 1000 base F gigabit Ethernet options offer very viable desktop fiber network connections. And of course, not many users currently need that kind of the speed of gigabit, but certainly the network manager and the boss do. Equipment interfaces are the switch hub fiber connections and the network adapter cards and workstations, servers, and routers. And all these types of equipment now offer fiber interface options. The cost of the interfaces is a matter of supply and demand. The LED optics used with 100 base FX are relatively cheap. Consequently, the adapter cards and hub interfaces are within reach of the high-end copper counterparts, or the high-end copper counterparts. Gigabit Ethernet is somewhat in transition as copper cabling options are emerging. Now, although the cost of fiber and copper gigabit Ethernet interfaces will be about the same initially, you can expect the price of the copper interface to drop considerably, even though the innovative VCSEL laser diodes that are used with gigabit Ethernet fiber are much cheaper than the older technology that they still represent, and that they still represent a significant cost penalty over copper transceivers. The installation efficiency and cost of centralized fiber cabling may actually be a compensating factor in considering fiber to the desktop. In very large installations, the savings of using centralized fiber over structured copper may be sufficient to dictate its use. In addition, there are inherent advantages such as interference immunity, security, and higher bandwidth, future technologies that may give fiber the upper hand. Copper to fiber conversion. It is practically impossible to entirely avoid the use of copper interfaces. Many types of equipment, such as printers and routers, may offer only copper interface options. It may be possible to use switches and hubs with both types of connections. The desktop workstations and servers are connected normally via fiber, and the incompatible equipment is connected to a switch or a hub with an appropriate copper interface. In cases where the hub conversion method is impractical, you can simply use a fiber to copper converter. You have several options on fiber to copper conversion. At 10 meg Ethernet, you can convert from fiber to an AUI, coax, or 10 base T connection. The AUI, or attachment user interface, is convenient because the interface includes a power source for a transceiver, which can be used to power the converter. In all other cases, you can expect to use one of the boxy wall plug transformers and a power cord to the converter. Pay particular attention to the type of fiber optic interface on the converter. The 100 meg fiber optic interface is now available in either FX or SX versions, and the wavelengths are totally different. Likewise, 10 base FL and FB are available, although the FB variety is quite rare. Gigabit Ethernet fiber interfaces are likewise available in several varieties of wavelength and mode, so pay attention to the needs of your equipment and/or fiber cable when you're making your choice. In addition to the copper to fiber converters, fiber mode converters are available. As the figure shows behind me, because of the common connectors, nothing physically prevents the interconnection of single mode and multi-mode fibers. However, the connection will cause an excessive transmission loss if the optical direction is from multi-mode to single mode. There is still an unexpected loss from single mode to multi-mode, but it is not as great. Consider that the transition from a large 50 UM fiber core to the tiny 4 to 8 UM single core obviously wastes most of the incident light, unless you are fortunate enough to be using a laser source that was inadvertently positioned or it has inadvertently positioned the beam to the center of the multi-mode core. Mode converters typically put a pair of wide bandwidth transceivers back to back in a box. One set of optics in single mode and the other in multi-mode. In between the interfaces is the proper electronics to repeat the signal to the opposite interface. For this reason, you can expect fiber mode converters to cost several times more than a simple fiber to copper converter. Now if we look at some of our installation practices. This section will briefly describe some of the installation requirements for fiber optic cable. Optical fibers are very widely in construction, unlike their copper counterparts, and this is due in part to the fact that a complete fiber circuit requires only 2 strands. One pair, although not twisted, we hope. Thus, the simplest fiber link could be 2 fiber strands with as little as the primary coating protecting the fiber. Conversely, a fiber link could be the same 2 fiber strands, but with tight buffer, strength members, thick jacketing, and even armor or embedded steel cable. The first cable type would need several types of protective routing devices, while the second type would need virtually none. If we look at the fiber cable protection, the degree of fiber cable, physical protection the fiber link requires depends on 2 factors: construction of the fiber cable and location of the cable run. In a fiber distribution panel, very little is needed in the way of physical protection for the fibers. What is needed is some type of fiber management and fiber storage. On the other hand, fibers that are used for horizontal or backbone runs do need more protection. These fiber runs will require the use of moderate jacketing trays, raceways to provide the appropriate amount of additional physical protection. Blown-in fiber places relatively unprotected strands inside plastic tubes that have been pre-installed between the TR and the work area. The tubes are technically raceways. They must meet all the flammability and smoke requirements of any platinum-rated device, if necessary. Likewise, the enclosed fibers must be appropriately rated for the installation location. Another type of protective fiber raceway is called an interduct. Now, interduct is used in applications where several fiber cables must be protected, as the figure shows behind me. The raceway is generally a ribbed construction to allow it to easily bend in a fairly large radius without collapsing the interior, as a smooth tube would easily collapse. The ribbed construction also provides mechanical strength against crushing. Interduct may be placed inside larger structures called ducts that are basically round or square pipes that run between buildings. The interducts are used to subdivide each section of the larger ducts and also to provide additional protection of fiber cable that is run through the duct. The interduct is an obvious choice for riser cables between building floors or between TRs on the same floor. Interduct is also very useful for the horizontal run between a TR and a consolidation point, as interduct may also be used in a cable tray to isolate fibers from fiber cables. A major advantage of the interduct is that it can be installed before any fiber is run, so you can simply route the interduct to wherever the fiber needs to go and then later pull the fiber in and terminate it. This prevents possible damage to pulled fiber during new construction build-out. As with all cable components, interduct must meet all the proper ratings to be placed in the plenum space. Cable trays are used to help organize and protect cabling infrastructure in horizontal runs. They may be used in any size installation, but are often found in large buildings. They serve to protect all types of cable, but they are useful as an alternative to cable hangers that place hundreds of bends in cable runs. The cable lies flat in the tray and is easily pulled straight across the long distances without the need for special devices such as pulleys. Additional cable is easily placed in the trays as needed. Cable trays are virtually mandatory in medium to large TRs. Trays are available in plastic or metal construction and must meet the small plenum requirements as cables. Corners and bends will require the use of a cable pulley when cables are initially installed. Fiber terminations. The physical termination procedure for optical fibers varies enormously with the particular type and brand of fiber connector that you're using. Accordingly, we will not cover all the options here. However, there are some common concepts that we need to cover briefly so that you will understand what is required for this complex operation. All fiber termination requires the preparation of a bare fiber for assembly within an appropriate connector. The outer jacket and fiber's plastic strength members must be removed if you're using a jacketed cable. In this type of cable, the outer jacket is slid around the circumference and slipped off the end of the cable. Next, the Kevlar fibers are combed to one side and then cut off at the edge of the remaining jacket. Fibers are extremely fine and a high quality cross cutter must be used to cut them back. The buffer coated fiber or fibers must now be prepared. The tight buffer is removed with a tool that is essentially a wire stripper. The buffer stripping tool is often a fixed opening tool that is specifically designed for the diameter of the bare fiber core and cladding, so that the fiber is not nicked when the buffer is removed. Any nick will severely compromise the flexural strength of the silica fiber and may result in spontaneous breakage. The rule of thumb is that such a break will always occur at the last possible moment, so that the installer will have to start over totally. So the lesson is that no nick is a good nick, or nothing can truly be done in the nick of time. The fiber is now trimmed to the proper length, usually with a tool that purposely scores, it nicks it, the fiber and then breaks the unwanted portion away from the remaining fiber. The breaking process is called cleaving the fiber, and it should leave an orthogonal break at the fiber end. This brings some basic rules of optics into play. First, if this break is not precisely 90 degrees, the light will exit the fiber at a slight angle. And second, the break is never exactly 90 degrees. The cure is a quick termination connector. Is to place the fiber end into a matching fluid so that the off-axis break has virtually no effect in a so-called field termination connector. The fiber end is inserted through the connector furrow so that it protrudes slightly from the end of the furrow. The fiber end is then polished down until it is exactly flush with the end of the furrow and consequently precisely square with the fiber. Final assembly is done by inserting the fiber into the connector and then securing the fiber mechanically, as shown here behind me. The older connector types, such as the SMA and the ST, generally require the application and curing of epoxy to secure the fiber to the connector. Newer quick termination connectors of this generation use the mechanical crimping in place of the epoxy. Both quick termination and field termination methods are available for most of the new stock connectors, including the SC and SFF connectors. An individual connector is designed either for quick or field termination, so you must obtain the appropriate connector for your proposed application. You should be aware that there might be significant difference in the expected connector losses between the two termination methods. For example, the Avaya, formerly Lucent Technology, one of the SFF manufacturers, offers a .2b or 0.2b dB loss expectation in their quick termination LC connection. and achieves half that 0.1 dB with the field termination. So field termination offers better potential results, but may require more training, special equipment, and take longer to install. It's not to say that an inexperienced installer cannot achieve higher losses than the norms, so specific manufacturer training is quite appropriate. A horizontal or backbone fiber run should be terminated in the same style of connector at either end, unless there are compelling reasons to do otherwise. In most cases, fiber cabling runs should terminate in a patch field in the TR. The patch panel to the equipment cord is the appropriate place for cable to adapt between different connector types. For example, an SC equipment connector could easily be interconnected to an SFF connector patch panel with an appropriate adapter cord. Likewise, the same type of transition could be made at the end user cord. The SFF connector types offer so many varieties that an abundance of adapter cables will be made available. In addition to adaptation to the legacy connectors, which would include the 568SC, cords must be available to transition between each of the popular SFF types. It would be wise to try to minimize the number of combinations of connectors by evaluating the types of connectors that are generally available on the networking equipment that you'll be using. The higher density devices will gravitate toward one of the SFF connectors. Thus, hubs and switches in the TR will tend to use an SFF connector to achieve maximum connection density on the workstation, workstation's net. The connector density is not an issue, so the decision to use an SFF connector will be the manufacturer's discretion, although there is a battle among manufacturers to control the fiber connector type in the horizontal cable plant. It is not at all clear that network managers will make equipment decisions solely on the basis of connector type, since the horizontal runs rarely terminate directly in the network equipment. An adapter cord can easily be used no matter what connector is needed, as the number and types of fiber optic connectors diverge. Proper installer training is very important. Many of the connector designs are distinctly non-intuitive with respect to assembly. In order for the connector to operate accordingly to its specifications, all the installation practices must be controlled right down to the millimeter. Connector designs are very different from one manufacturer to the other. Installers should be trained on the connector brand that they're installing, and the network managers should require training and certification of their installers and contractors. Now, while this is not rocket science, it is certainly not simple, and the quality and longevity of your fiber cable plant may well depend on the quality and consistency of the installation. Fiber optic cable installation requirements call for the storage of extra fiber at the point of termination. The reason for this is simply to allow future connector changes and for the re-termination of fiber due to potential breaks after installation. The extra fiber must be stored in a manner that protects it from damage. At the work area outlet, the cable could be theoretically be coiled up into a recessed outlet box if one is being used. However, LAN wiring is often done with outlet rings that are totally open to the wall space. As we talked about in Chapter 6, we showed you a picture of that. Now, a safe alternative to use is one of the special fiber outlet boxes mounted at the surface of the wall and contain a means for storing and protecting the fiber strands, as shown here, and as well as we showed you in Chapter 6. Then we get to the fiber optic testing. Now, once installed, the fiber must be tested to determine proper operation. Simple connectivity may be determined by a simple source and detector arrangement, much like the basic continuity test of copper cable. The simple source is a flashlight, possibly with a fiber cable adapter, and the simplest detector is the human eye. Now, following the safety practice in the next section, we be certain that you know that a low power visible light source is being used for the test, and even then, don't look directly into the end of the fiber. However, as with copper cable, a much more complex test is needed to determine proper operation of the fiber link. Now, this is accomplished with a fiber optic cable scanner, just like the one shown behind me. In some cases, the scanner may be an adapter module that is used with a copper cable scanner. However, because copper scanning is inherently more complex and expensive, and because different cable crews may be involved in installing fiber optic cables, you may want to purchase a separate fiber optic tester. Now, all fiber optic cable testers for field use have a local and remote unit. The local unit sends light of a known intensity down the cable under test. The remote unit senses the absolute magnitude of the received light and then calculates the loss. A pass-fail indication is made and may be a function of the length of the cable. The remote may be totally passive to the installer and simply report at the results of the local tester. The two units may be interchangeable or at least have dual displays, so the installer at the remote end knows what's going on. Many of the tester pairs have microphones or headphones and an optical order wire so that the two installers can talk when connected to the same cable. Testing installed fiber cable is a matter of measuring the link loss. In general, if the link loss is within budget for the standard and with stricter link budgets for certain applications, your cable is fine. You should really test all the appropriate wavelengths for the application, and the tester should use a time domain reflectometry, or a TDR, to ensure that the cable length is within the prescribed length on its distances. Some more sophisticated testers may ensure that return losses, a measure of reflections, are within the limits. But if you use appropriate cable and connectors, that should not be a problem. A really sophisticated test would be to measure the link's bandwidth length product, and it would catch cables that have insufficient bandwidth for a gigaspeed operation at their extended distances. Most fiber optic testers use the overfilled launch testing method, where the entire fiber core is flooded with light, usually from an LED source. This method is effective in dealing with 50 and 62.5 core diameters. In testers that use a VCSEL diode source, a mode dispersion technique is used to avoid the mode blockage that can occur in some multimode fibers. You should be aware that this testing technique can mask some problems that may be experienced when you actually hook up the cable run to a piece of equipment. Be aware of the specifications and limitations of your particular tester. That takes care of this basic pass-fail testing of the fiber optic link. Troubleshooting a marginal or failed link is a different matter. One of the problems you encounter with a failed link is determining where the failure is located with respect to the cable ends. This issue is a problem whether you're troubleshooting newly installed cable or a cable that's been installed and has been operating for some time. Your tester may be able to function as a field TDR in addition to the basic loss measurements. If so, it's simple to determine the location of a fiber break or a botched connector installation. Knowing which connector is bad or where the fiber is damaged saves a lot of time in repair. Fiber breaks are permitted to be spliced because splices have inherently low loss. Bad connectors should simply be replaced, so be thankful that extra fiber was left at the point of termination. Safety considerations. Fiber optic technology has safety aspects that are quite different from those of copper cabling. As long as the proper procedures are followed, fiber optic installation should be as safe as any type of cabling. Eye protection in the form of safety glasses should be used for all fiber assembly work. Chemicals. Firstly, all types of fiber optic termination use some type of chemical. The older epoxy style connectors use a harsh two-part resin and hardener combination that can harm skin, clothes, and eyes. And some of the newer field termination connectors, connection designs always prefer the removal of any glass particles that are in the eye to a qualified medical practitioner. Now let's talk about laser safety in the class of operation. Many optical transceivers that are used in optical networking use laser diodes for their light sources. The wavelengths of the lights that are used are in the infrared range, which are beyond the range of human sight. However, light in these wavelengths could still be harmful if sufficiently intense. All the optical sources that are recommended for fiberland operation are operated at class 1, at power levels below that considered to be hazardous. However, other classes of laser operation exist, and you should be aware of their relative dangers.
Bending the light using water, a cool science experiment with a laser. All our school life, we've been taught that light travels in straight lines. Well, here's a cool experiment that'll prove that light can also bend, or so you can make people think. For this experiment, you'll need an empty water bottle, water, a screwdriver or any pointed thing, a laser, and a bowl. Procedure. Take the empty water bottle and punch a hole on the surface of the water bottle. Make sure that the hole is made in or around the midway of the bottle. Put the bottle in the bowl and fill the bottle with water. You'll notice that the water starts flowing out of the bottle through the hole. Now, using the laser, project the beam horizontally towards the hole from the other side of the bottle. Notice that the laser beam follows the laminar flow of the water stream, and the beam crashes down along with the water into the bowl. Explanation. First things first, in this experiment, technically the light does not bend. Observe the laminar flow of the water stream coming out of the bottle. When the water is in laminar flow, the water stream acts just like a fiber optic and carries the light. When the light beam hits the water stream, the laser light gets reflected inside the stream. Remember, the surface of water is reflective both on its surface and below the surface. This underside reflection of water is usually seen in darkly lit environments like a fish tank. When light leaves a denser material, in this case water, due to the change in speed, it will change directions. However, when a certain angle, called the critical angle, is reached, it reflects back. The critical angle is the smallest angle of incidence for which light is totally reflected. Total internal reflection is a phenomenon that happens when a propagating wave strikes a medium boundary at an angle larger than a particular critical angle with respect to the normal to the surface. The critical angle of water is 48.8 degrees. When the angle of the beam crosses the critical angle, the light does not go out of the stream and total internal reflection takes place. At the end of the stream, there is a lot of turbulence, so the continuous reflection chain breaks or scatters down and the laser light gets scattered. Because of this phenomenon called total internal reflection, the light appears to be traveling along with the water stream. Remember to like this video and subscribe for more cool science.
Fiber is definitely in our future. Now that concludes this lesson on fiber optic basics. I know this was a crazy long one, but move on over to the online assessment portion of our system. Then I'll see you in class. We'll watch a demonstration by Corning on fiber optic termination, and that's all for now. See ya.